Good day, everyone. This time, I will going to discuss part, part 3.a on set notations and subsets of part 3, language of sets, in chapter 2 module, mathematical language and symbols. The required readings is a set of real numbers, set notations, set operations, and symbols. So the knowledge on different sets of numbers and its notation will help students to describe and specify a given set. So you may recall the sets, the subsets, and the intersections and the union of the set of numbers. So we have Z0, and we denote this with Z0. And we have the set of natural numbers, and we denote this with capital letter N. The union of 0 and the set of natural number is equal to the set of whole numbers, and the set of whole numbers and the set of negative integers is the set of integers, and the set of integers and the set of non-integer rational number denoted by set K is the set of rational number. So, as you see, the diagram shows the set of numbers in each boxes. And then the connection shows the subsets, the union in the intersections of the given of set of numbers. So, the subset of integers denoted by capital letter C are the set of negative integers, the set of whole number, and the subset of whole number is 0 and the set of natural numbers. Then, set K is the set of non-integer rational numbers. What is this non-integer rational numbers? These are the positive and the negative fractions and decimal numbers. So the union of the integers and the non-integer rational number is the set of rational number. The set of rational number and the set of irrational number in symbol, we have letter H, the union of these two is the set of real numbers. In notation, we generally use capital letter R. And the set of the real number and the set of imaginary number in symbol, we use small letter I. The union of these two is the set of complex numbers. So, this is how do we denote the set of numbers. So, as you notice, a separated box means it did not have a common point of intersection. So, the connection of the box tells you all about the subsets, and at the same time, the connection of the box tells you all about the union of sets. Let's go now to what a set is. We are talking all about set. Set is a collection of well-defined objects. So that, what do we mean by well-defined object? It simply tells you that when the set is or is well-defined, you know what the objects do belong and you know what the objects that do not belong on the given set. And set is completely determined by what its elements are, not the order in which they might be listed or the fact that some members or elements might be listed more than once. Set notations. We denote set by a capital letter. Enclosed a grouping symbol are the list of elements or members separated by commas. Enclosed the grouping symbols are a description, a rule, a definition, or a set builder notation that describe the set. A set can also be described, defined, and illustrated using Venn diagram. Set S here is a Venn diagram, and Venn diagram uses polygonal shape to describe and denote sets and to work on operation of sets. In our example, we have set S is equal to 1, 2, 3, 4, 5, or the elements or members of the sets are the numbers 1, 2, 3, 4, 5 using roster notation. We use roster notation to denote a finite kind of set. A finite kind of set is a set that has a countable number of elements. Set S here is also a set of natural number less than 6. So in this notation, we use a definition or description or rule method to describe or denote the given set. And generally, we use the rule, the definition, or description method to describe or denote an infinite set. An infinite set. So that an infinite set is a set that has uncountable elements. That's why we use description and definition to describe a given set. For both finite and infinite, we can use a definition or description or rule method. But roster method is for a finite set only. Set S is equals to S, which is an element of natural number such that S is less than 6. This is a set builder notation used to define, to describe a numerical kind of set mathematically. Then, a member or members or elements of the set is denoted by the symbol Greek letter E. Set cardinality is the total number of elements in a given set, denoted by N of S. In the previous example, N of S is equals to 5. Let us come with the given examples below. Set A is equals to the set ABC, where the cardinal number of A is equals to 3 and the elements are A, B, C. Set B is equals to say AB, where the cardinal number of set B is equals to 3 and the elements are A, B, C. And set C is equals to A, B, B, C, C, and C, where the cardinal number of set C is equals to 3. Since for a set that their element is listed twice or more than one, we only count that element once. So the element of set C is set ABC. You will notice that set A is equal to set B and is equal to set C because they have the same cardinality and they have an identical elements. Set D is equals to set 1 to the elements of, or to set D is equal to the set of one element and set 1 as an element. So the cardinal number of set D is equals to 2 and the elements of set D are 1 and set 1. Remember this term set 1. For set E is equals to set of 0, the cardinal elements of set D is equals to 1 and the element of set D is 0. F is equals to the set of X, set of XY, and set of Z. So the cardinal number of set F is equals to 3, where the elements are X, set xy, and set z. I repeat, the element of set F are x, set xy, and set z. Set G is equals to Q. What is Q? Q is the set of rational numbers. So the cardinal number of set G is infinite. For set H is equals to set of cut with horn. So the cardinal number of set H is equals to empty. The element of set H is empty because it has no member or it has no element. Unless otherwise, your cat has a horn. Then, let's go to set operation. Subsets and proper subsets. We do have the symbol for subsets and proper subsets. We have set A illustrated or presented in a form of a diagram, and we call this Venn diagram. Set B contained in set E. Set B has an element x, y, z. So we said set B is a subset of A. B is a subset of A if and only if X, which is an element of B, implies that X also is an element of A. Or for all X, which is an element of B, then X is an element of A. So this means B contained in A. B is inside an A. B is a part of A and in fact inside A. That's why we call B as a subset of A. And the second illustration, B is a proper subset of A if and only if there exists at least one element of A not in B. B has an element X, Y, Z. And outside B, as you see, we still have an element that is A, B, C. So B, the elements of B, we have X, Y, and Z. If B contained in A, or if B is in A, we call B complement. These are the elements of A not in B. B complements are the elements of A not in B, and we have A, B, C. So N of B complement is 3. So B complements, these are the elements of B not in A. Elements of A not in B. So if we need only at least one, but we have 3, then therefore B is a proper subset of A. What does it differ if we do not have a subset, or if we do not have elements in A but all the elements are in B? In this example, you will notice that B is a subset of A. B here is a subset of A since B contained in A. But what are the elements of B? B equals XYZ. So kung nasa loob ng A ang B, what are the elements of A? A is equals to XYZ as well. So you will notice here that B is equal to A. A is a subset of B and B is a subset of A if and only if A is equal to B. So that's how do we differentiate a proper subset to a subset. In this case, B is not a subset of A. Why? B is not a subset of A because there exists an element in B, not an A. So to become a subset, B must contain an A. So here it is but a joint set, but an intersection of set as well because there they contain only common elements. But B is not a subset of A because X here is an element of B, but X is not an element of A. Then, Y is an element of B and Y is an element of A. So XY here is an intersection. X and Y are common elements of A and B. And B, but not X. These are but joint sets. Okay, with the point of intersection. This one is their point of intersection, but it do not contain. In addition to, an empty set is a subset of any set, and all sets are subsets of themselves. So the next one we have disjoint sets. If we have joint sets, we have disjoint sets. These sets are totally do not have common elements. That's why we call this disjoint sets. So here, X is an element of B but X is not an element of A. A is an element of A, but A is not an element of B. So these sets are totally disjoint. So we cannot say any subsets of these two, or a relationship of subset between these two. Distinction between elements and subset. For letter A, 2 is an element of set having an elements 1, 2, 3. For letter B, set 2 is a subset of 1, 2, 3. To become a subset, you must put 2 as a set. So this is correct. Letter C, set 2 is not an element of set 1, 2, 3 because to be an element must not be a set. It must only be 2 as an element of set 1, 2, 3 as in letter A given. So 2 must not be enclosed in a set or in a grouping symbol. Set D, set 2 is not a subset of the set having an element set 1 and set 2 because set 2 is an element of the given set. Instead, maybe to make it true, you might put this in a set. So you might have set of set 2 is a subset of the given set. In letter E, 2 is not a subset of set 1, 2, 3. Why? Because 2 is an element. To make this statement true, that 2 is a subset of 1, 2, 3, then you must put 2 in a grouping symbol as a set. Okay, I hope so it's clear. So the next topic now would be the part B, which is more on set intersection. So that ends up the part A that is more on set notation and first part of set operation.